Okay, well, we'll pick up the lecture here at the middle of our set of slides on ancient, or I guess early Babylonian mathematics. So we're going to learn a little bit today about Babylonian geometry, and one of the sources for our knowledge of what Babylonians knew about geometry is a special clay tablet referred to as Plimpton 332. It's dated between 1600 and 1900 BC. It was just recently deciphered I guess, in a relative sense, in 1945. The contents of the tablet, once deciphered, drew into question the authorship of a well-known mathematical theorem. So on the tablet, we find three columns of numbers. The first two columns are headed by the words that scholars believe translate to width and diagonal. And the question I have is, what conclusions can we draw from this ancient table? So that's the question to be investigated. Let's go ahead and take a look at the table of values. Here they are. So once again, we have three columns. So one column in the middle column and a third column. And we think that the headings of the columns here would be width and diagonal for the first two columns. And so just upon first investigation, I can see that all of the numbers in each row, the left-hand value is less than the right-hand value for every single entry. I should say a little bit about how the text formats these. The numbers written in parentheses, this is directly from your text. The ones written in parentheses are the original numbers appearing on the tablet, while those written next to them, we believe, are the intended numbers. And each one of those errors is explained in your text. And we think most of them are due to copying errors that are associated with the scribes who would have been in charge of writing these. So you can read a little bit about those errors, but let's just assume that the historians have it right, that those numbers that are written not in parentheses are those that were intended in the original tablet. And if we think in terms of width and diagonal, if that's what we really believe these to signify, then it might make sense that, seeing how so much of early geometry had to do with rectangles, we could be talking about rectangles, widths, and diagonals. So let's just take the case of 119 and 169 and investigate that a little bit. So if we're talking about 119 and 169, so what might we be talking about here? So I would assume that what we'd be talking about is some sort of a diagonal of a rectangle. So let's take a look at a rectangle and draw one up and think about it a bit. So I'll draw up a little rectangle and think a little bit about what we have here. So if we think that 119 is some sort of width measurement, and 169 is some sort of diagonal measurement. Then I guess what we might be interested in checking is to see if there's some sort of relationship here to this missing side. That's my question, at least. So if we call the missing side x, the equation that we would solve to find x is, of course, that which comes to us from the Pythagorean theorem. 119 squared plus x squared equals 169 squared. And let's see, let's get a calculator out and take a look. So to solve that for x, of course, I would take 169, square it, subtract 119 squared, and I'd get x squared would be equal to 144, I guess 14,400, and then of course I would take the square root of my answer there, and looks like the square root of that answer is 120. So our value here of x is 120. And if you're familiar with the Pythagorean theorem, you recognize that what we found here is a Pythagorean triple. That is three rational numbers, or in this case whole numbers, that actually work to construct a right triangle. So we would identify here that what we have is the Pythagorean triple 119, 120, 169. Oh, got a bad pencil lead here. Okay, let's try this again. Pythagorean triple. So what some scholars immediately noticed was that, well, that first number, if we put it in, the first pair of numbers, if we put them in as a diagonal and a leg of a right triangle, what results when we apply the Pythagorean theorem is another integer, which if you've played around a little bit with the Pythagorean theorem, you know that that just doesn't happen very often. And so it might be worth checking some of these other numbers. So the next set in the list would be what is it, 66,049, and I guess the way that we would think of this would be 66,049 squared plus, let's call it x squared again, is going to be equal to 40, oh, I have it backwards, sorry, that would be the hypotenuse. Let me just go back really quick and take a look at what that last, there it is. So let's skip the one that has been corrected and go to this one. So we would think that 4601 and 6649 would be the two numbers in question. So 4601 and 6609. So the check would be 4601 squared plus x squared equals 6649 squared. Well, so if I solve for x here, this turns out to yield an x value of 4,800. So again, another Pythagorean triple has been found using the two numbers provided in the table. The triple would be 4601, 4,800, and 6649. And indeed, if you try this with the next one, for example, if we step out here and take a look at the next one, I'm going to skip down a few levels and take a look at 96, 97, and 65 and see if that's indeed, see if that is indeed a triple as well, 97 and 65. So it would be 65 squared plus x squared would equal 97 squared. And here, if we solve for x, what you'll find out is that 72 results. So again, we found a triple: 65, 72, and 97. And indeed, all of the numbers in the table, if we accept the scholars, historians, I guess, corrected version of the table, produce Pythagorean triples. And this has been somewhat of a controversial find because, of course, this tablet predates Pythagoras by nearly 1,000 years, I believe. So it's drawn into question whether or not the theorem attributed to Pythagoras was truly his own invention. Now, one of the things we can see by the virtue of the fact that triples were sought in this table is that no evidence of knowledge of irrationality that results from the Pythagorean theorem, what we know to be irrationality today, was evidenced in the tablet. And furthermore, it seems that there's been lots of speculation about, well, how did they get these numbers? Obviously, there's some really big ones. For example, 12,709, 18,541, very large numbers that certainly couldn't be arrived at by guessing and checking, or if they were arrived at by guessing and checking, it would indicate extreme searching effort. And so there's been lots of investigation into, well, how did the Babylonians arrive at this this list? It certainly seems like it wouldn't have resulted through a process of just empirical investigation, that rather there must be some sort of Pythagorean triple generating activity that underlies the creation of this series of Pythagorean triples, or I guess two parts of the triples. And so let's take a look at the most common generator, and for Pythagorean triples, I'll go ahead and derive it for you and see if it might be informative in terms of whether or not we have some evidence that the Babylonians were aware of Pythagorean generating algorithms. So, so let's take a look at a triple generator. And see if we can derive this. So the idea is that what we're trying to find is an x squared and a y squared that sum together to make some z squared, where x, y, and z are all elements of the positive integers. So we'll call that z star, plus, since we're talking only about positive distances. So one of the things we can do right off the bat is try to get some sort of a ratio going here. So what I'm going to do is I'm going to divide our initial equation by x squared, and when I divide by x squared, I get 1 plus y over x quantity squared plus, or excuse me, equals z over x quantity squared. So we'd have that result at this point. Which can be then rearranged to make a sum that, or excuse me, a difference that equals 1. So that would be, if I subtract y over x from both sides, I get a 1 equals z over x squared minus y over x squared, which rearranging going to be a little bit easier to work with this with the 1 on the right hand side. So I'll write it as z over x quantity squared minus, excuse me, y over x quantity squared equals 1. Okay, so let's go ahead and introduce some new variables. Really, so what we're looking for are two rational numbers whose squares differ by 1. So two fractions whose squares differ by 1. Let's let the first fraction be called alpha. That's going to be our z over x. And let's let the second rational number be called beta, so that will be our y over x. Now, I just want to draw into your attention to the fact that we can solve for z and y here. So z would then be equal to alpha x, and y would then be equal to beta x. And we're going to come back to this fact later, but I want to just draw your attention to it at this point. So the one thing I do know is that alpha and beta are elements of the rational numbers now, so we're talking about rational numbers, and furthermore, they're positive rational numbers by virtue of the fact that x and y and z are all positive integers. Okay, so off we go to the races. If I make this substitution, the z over x, that leaves my equation now to be alpha squared, and the y over x, which is this term up here, would be beta squared. The difference of those two is 1. And so what do we see? We see that we can now factor this as alpha plus beta and alpha minus beta have to be equal to 1. Now keep in mind that alpha and beta are both elements of the rational numbers. So if we think of these being elements of the rational numbers, then the sums are elements of rationals and the differences are elements of rationals, no longer necessarily positive rationals, but definitely part of the rationals because they're closed under subtraction. So what do we have here? This is the key to the proof. These two numbers, the alpha plus beta and the alpha minus beta, must be reciprocals. The reason they have to be reciprocals is because their product equals 1. So that means that there is some rational number, m over n here, whose reciprocal is n over m here. That's kind of interesting. So let's go ahead and move on. So that means we could assign certain values for their reciprocals. Let's go ahead and do that. So let's let m over n be equal to the first one, alpha plus beta. And let's go ahead and let n over m, the reciprocal, be equal to the second term, so the alpha minus beta. So we're just literally replacing these two terms with a representation that is a reciprocal representation, and now we can say that both m and n are coming from the integers. So where are we at? Geez, this seems like we've done two variable swaps, but we're getting close now to the answer because we have the ability now to make some eliminations. So one thing we can do is we can add these two equations together. And when I add these two equations together, I get 2 alpha is equal to m over n plus n over m, which then will produce, I guess if I find a common denominator here, um, this would be the same thing as m squared plus n squared all over mn. And solving for alpha then would be just dividing through by 2. So alpha would be the same thing as m squared plus n squared all over 2mn. Okay, so that gives us a way for calculating alpha. Let's see, let's try beta now. If I wanted to isolate beta, what I would do is I would subtract the second equation from the first. So what would result then would be 2 betas, because subtracting alphas would get rid of them, and then I would have that equal to m over n minus n over m, which finding a common denominator here would be again m squared, but now minus n squared all over nm. So something pretty similar here, difference of just an operation, addition here, subtraction there, which then leads to a value for beta, which is just dividing through by 2. It's going to be equal to m squared minus n squared all over 2mn. So we've got an alpha and a beta. But keep in mind that now we can go back and talk a little bit about, what we know about now that we know alpha and beta. We know that they relate, kind of the three partners in our original question, the x, y, and the z. So if I know how to construct alpha and I know how to construct beta, then I know how to construct z and I know how to construct y. So let's go ahead and see how we would have to construct z. So by substitution, we could say that z has to be equal to alpha x. So it has to be equal to, well, alpha is this term, so m squared plus n squared all over 2mn all times x. And then let's see, y has to be equal to beta x. So it would be equal to m squared minus n squared all over 2mn, and that's times x. So now the question, and this is the one that I would ask in class, if we know x and how to create it, and especially if we know how to create it in terms of m's and n's, then we would know how to create z's and y's. So the question would be how to choose x such that z and y are guaranteed to be integers and positive integers even, right? So that's the real question. So how would you choose x so that your z and your y would be an integer? And when you look at this, you can see, well, I've got a rational number here. So if I want it to be an integer, then I need to choose x very carefully because I want to eliminate the division. And so at this point, I just want you to think about it. I'm going to give it a 15-minute or 15-second wait time. How would you choose x so that z and y would be guaranteed to be integers? Well, I hope that you came to the conclusion that choose x equal to 2mn. So if you can see that if you chose x to be equal to 2mn, then we would have cancellation top and bottom, and y would be guaranteed to be an integer, and z would be guaranteed to be an integer because both m and n are integers. And we would just have the sum of the square of those two integers and the difference of the square of those two integers. So this is precisely the conclusion of the most common Pythagorean generator that's widely attributed to Eudoxus, I think, is the person who in the 1st or 2nd century who is credited with this Pythagorean generator. What you do is you choose an m and an n in the positive integers, and then you generate a Pythagorean triple by letting x be equal to 2mn, let y be equal to, let's see, m squared minus n squared all over 2m, excuse me, that's it actually, because they cancel. Y will be equal to m squared minus n squared, and then z, the hypotenuse, will be equal to m squared plus n squared. So this is a standard procedure known for a couple thousand years at least about how to generate Pythagorean triples. So let's just give an example. If we choose, let's say, let's pick something difficult. What if we choose m to be equal to 7 and n to be equal to 4. Okay, so this is, again, I'm going to show you an example. If m is 7 and n is 4, then what would x be? X would be 2 times m times n, so 7 times 4, so 28 times 2, that would be 56. Let's see, y would be equal to m squared minus n squared. So let's see, m squared is 7 squared minus n squared is 4 squared. So that will be 49 minus 16, 33. And then the last one would be z, which would be equal to 7 squared plus 4 squared. So that's 49 plus 16. You'll get 65 there. And supposedly this is going to be a Pythagorean triple. And indeed, if you check it, it does work. You'll get 56 squared plus 33 squared does equal 65 squared. So that will check. And what's interesting about this is that, I guess history has given us the knowledge of this particular Pythagorean generator. And of course, what we want to know is perhaps was this the machinery that the Babylonians had access to generate their list. And your text does actually go into this issue in the page after, presenting. We can see that if you choose m this way and n this way, so 2 to the second times 3 and 5, then what you generate is 120 and 19. And in fact, these are all of the pairs that we find in the list in the first two columns. Excuse me, this would be column 1 of the list, and this would be column 2 of the list. And these would be the numbers necessary to generate them using the well-known Pythagorean generator. And there is some discussion of whether or not perhaps this is what was going on to generate the list. Some interesting, I guess, anecdotes looking at this analysis of the Babylonian Plimpton 332 tablet is that if they were aware of this generator, then all generators M and N that they chose were some combinations of 2, 3s, and 5s. So we don't, for example, see any generator that includes a factor of 7 when it's primally decomposed. So perhaps there was some limitation in the scribes or mathematicians' choice of integers to use in generating. I personally feel like it's fairly weak evidence that they were knowledgeable of the Pythagorean triple generator that we see written above each of these 3 columns, but we'll leave it up to you to decide what you think. So Babylonian geometry, definitely some interesting things there with the Pythagorean triple analysis. They were certainly aware, or at least investigated, the relationship that we now know to be the Pythagorean theorem. Evidence that they knew the theorem also is exhibited in several other places in tablets. For example, we find this particular problem, a beam of length 0, 30, or what we would think of as 30/60ths, stands in an upright position against a wall. The upper end is slipped down a distance of 0, 6, or what we would think of 6/60ths. how far did the lower end move from the wall? That comes from a Babylonian tablet. Let's just sketch this so that we get a sense of what it looks like, um, and tell ourselves, I guess, investigate whether or not what we would need to solve this. So we've got this beam standing against a wall. So if we sort of sketched this in um, sort of before and after, so if this is my wall, let's say, um, and here I have the floor, then we have some beam. Let's just assume it's some sort of a wooden beam like this, standing against the wall, and we know that the length of the beam is equal to 0, 30, which we in modern notation would represent as, this is sort of like our decimal point, so it'd be 30 times 1/60th, because this would be the 1/60th place, so 30/60th or 1/2, so that would be the length of this beam. I don't know, what do I want to do? I guess I want to say that this is equal to 1/2 in modern terms, but we're told that it's slipped down the wall, so let's draw sort of an after picture. And my understanding is that slipping down the wall means it's starting to slip in this direction. So we'd have some sort of after picture that looks something like, maybe like this. The beam is now slipped down the wall to look something like that. Again, this is my wall over here. And what we know is that from the before and after, that it slipped down the wall a certain distance. And I guess if we kind of think of it this way, that distance is given as 0:6, which in our modern terms would be 6 times 1/60th. So 6/60th, or 1/10 of a unit, it slipped down the wall. So it slipped down the wall 1/10. And the question is how far out has it moved from the wall right here? And so what I'll offer, if you can solve this particular problem using the Pythagorean theorem and hand it to me on Monday after my absence, then I'll give you, let's say, 5 points of extra credit towards your quiz score, or I'll just say some extra credit towards your quiz score on Monday. Going back to the slides, we can see, let's do one more section on another mathematical papyrus that comes to us from Egypt. It gives us some insights into the conversation that's going on over the course of history between Egypt and Babylonian peoples in terms of the mathematical content. So the Cairo mathematical papyrus is dated to 300 BC, hundreds of years after the Rhind papyrus. And so we get a sense of the development of the mathematical knowledge of the Egyptians, and most certainly through their exposure to the ideas that are being developed in Babylonia. So let's take a look at a couple of problems. Problem number 1, we'll call it, that appears in the papyrus, says to find the length and width of a rectangle with an area of 60 units squared and a diagonal of 13 units. So let's take a look at how we might attack that problem. If I can get there it goes. We'll go ahead and see if I can't, there we go. Get this started. So what do we have? We've got some sort of a rectangle whose length and width are unknown, but we're told the diagonal is 13, the area is 60. So we can develop a few equations from the givens. We know that, well, I guess in the particular papyrus, the two equations that are developed are the same ones that we would develop in modern times. One is the theorem of Pythagoras, so it shows that they were actually aware of this. X squared plus y squared is equal to 13 squared, or 169. And then the second, of course, equation would be x times y would have to be equal to the area. The length times the width, of course, is the area of the rectangle, so xy equals 60. So kind of a curious problem, because in modern times what we'd probably do is develop some method of substitution to eliminate variables and get some sort of a quadratic equation and solve, or polynomial equation and solve it. But a very different solution method is used in the Cairo papyrus. That solution method takes this second equation and multiplies both sides of the equation by 2 to yield 2xy equals 120. And then this, let's call it equation 2 and equation 1. These two equations are added and subtracted to yield two different expressions. So if we add equation 1 to equation 2, then what we get is x squared plus 2xy plus y squared is equal to 169 plus 120. So that's going to be 289. And when we get to that stage in the game, what is interesting is that they actually recognize this as a perfect square polynomial, which can be rewritten as x plus y quantity squared equals 289. And if x plus y quantity squared is 289, then we simply have to find the square root to solve for x plus y, and the square root is readily found because 289 turns out to be a perfect square. So 289's square root is 17. And so we get one relationship that tells us that the sum of these two, the length and the width, has to be 17. The game is played similarly through subtraction. So if I take equation 1 and subtract equation 2, I get x squared minus 2xy plus y squared equals 169 minus 120 would be 49, which yields x minus y squared equals 49, which means that x minus y has to be equal to 7. And you can see that based on these two results that we can quickly say add the two equations together to get 2x equals 24, or x is equal to 12, and then back substitution will allow us to find that y is equal to 5. So kind of an interesting solution method. It shows that they've definitely advanced. First of all, the Egyptians now possess the Pythagorean theorem. Secondly, they're starting to recognize the role of polynomials in perfect squares in reducing complicated polynomial expressions. And then they have an understanding of what a square root is. It turns out the game is even more impressive here if we take a look at the next problem. The next problem is finding the length and width of a rectangle with an area of 60 units and a diagonal of 15 units now. So the only thing that's really changed here is that the diagonal went from 13 units to 15 units. So our analysis should be remarkably similar, and indeed it is in the papyrus, but one of the things that's interesting is that we get to a whole different endpoint. So here we'd have x squared plus y squared equals 15 squared. So that would be 225. And the second equation would be xy equals 60 as before, and 2xy equals 120 as before. Again, equation 1 and equation 2. If we add the two equations together, what we'll get to is a situation where we have, so I'll just say adding, what does it yield? It yields, well, we know it'll yield an x plus a y quantity squared, and 225 plus 120, what does that give us? That gives us 345. And subtracting is going to give us let's see, so an x minus a y squared equal to 105. And here's where things get kind of dicey, because what we notice is that up here we sort of had a nice number for whatever reason. We ended up with I guess a perfect square both left and right on the equation, so reducing the square root was simply finding the integer that squares to equal 289. Similar here for 49. Now, no integer squared equals 345, and no integer squared equals 105. So what we've stumbled upon in the Cairo papyrus is evidence of non-perfect square roots. And the question is, what did they do? What did they do to resolve that issue? And here's what they did. It's kind of interesting. So what they do is they did not really know how to handle these, so they would approximate them. And what happens in the Cairo papyrus is they take 345 and they rewrite it as the sum of the largest perfect square that's less than 345. Turns out that's 324. Make sure I write it right. 324, and plus whatever's left over, the 21. So they think of it this way as a perfect square plus something else. And, so that's, if we want to think of it, it's 18 squared plus 21. And indeed, we kind of think of it this way when we estimate square roots. We know this square root has to be between 18 and 19 now because it's a little bit bigger than 18 squared. And here's the approximation they make. They rightly call this 18 plus something else, but the something else that they use is literally this. It's 21, so this number, divided by 2 times 18, so twice that number. So they take 21 and divide it by twice that number. So let's go ahead and compute that number and compare it to the true square root's decimal value. We get about 18.583. I guess not about, exactly, that's 18.583 repeating. And if I take the true square root of 345 on my calculator, what you'll get is, well, I'm going to just put equal to, really. It's 18.57417562, ... And so you can see that they're remarkably similar, these two values, and so it seems like this estimate is really a good one. So let's go back and just kind of think about what's going on. Really what they're doing in approximating square roots, we know that if the number was not a perfect square, Babylonians and later Egyptians, and even later Archimedes, to whom this approximation is credited, are using this formula that if you want to find the square root of a number, you write it as the largest perfect square plus some extra, and then its square root will be that value a plus b divided by 2 times a. And let's demonstrate geometrically the error associated with that and end on that today. So we'll go ahead and bring up my image again and make it bigger. And so what's going on here, if what we're trying to find, if we think that a number can be written as some largest square plus b, and what we want to find is we want to find the square root of n, what's going on here geometrically? Well, so think about a as some area. I guess think about n as some area that can be written as a squared plus b. So the first thing we would think is that, well, I've got some a squared, right? So if this is a squared, here's a, and then there's some additional b here, right? But if I want to take the square root of a number, literally what I'm doing is taking the area and stripping off the side length of the square. So what we really want to do is we want to add to this square a little, I guess a little extra, because it's not, n is not just a squared, it's more, it's plus a b. And what we'd like is for this whole thing to be b, which would be kind of interesting if we could somehow cut this in half and use trapezoids and whatnot. But that's not actually the way they conceived of it. They thought, okay, well, what I'm going to do is I'm going to take the value b and I'm going to split it between this region and this region in the square. And so some simple algebra will allow you to find out what this side length is right here, because we know that this side length here is a, right? And we know that this side length here is a. And if b is akin to the area between these two, let's just call this x. So if what we're literally trying to find is what is x? Well, we know that x has to be equal to, well, let's see, no, we don't know what x has to be equal to yet. What we know is the area of these two have to be equal to b. So what do we have? We have 2 times a times x has to be equal to b if this whole thing is supposed to be sort of akin to approximately what n is. And so if we solve for x, x is going to be equal to b over 2a. So literally this thing is b over 2a, and this one would be equal to b over 2a. And this whole length then would be a plus b over 2a. So that means that when I take the square root of the number whose total value is a squared plus bx, excuse me, a squared plus b, what I'm doing is trying to find the side length of a square who has this area, and this square approximately has the area of n. Of course, we notice here is our error unaccounted for. And, and so taking the side length of a square is akin to taking the square root. And that is particularly the answer we were looking for. That's it for today. I'll be looking forward to seeing you on Monday.